Hi there. In today's webinar, episode 8 of this series in solar and battery training, we're going to look at arc flash incident energy calculations and also the restricted locations for the installation of batteries, particularly in residential applications. All right, let's get into it. We're going to continue on from yesterday, which was we were discussing AS NZS 5139, the new battery standard. Before I launch into it, I just want to introduce my colleague, Rachel, who's helping with this process. Hi, Rachel.
Hello, everyone. Welcome again. While I've got the screen, I'd just like to mention how to use your windows. At the bottom of your screen, you should see Q&A and chat. And if you have a question for Glenn, please put it in the Q&A and ask it as you think of it. It makes it easier to feed to him and manage, and it's easier to get all questions answered if you keep them coming as you think of it, rather than when you know he's answering questions. So, and if you want to make a comment or talk amongst yourselves, you can use the chat window.
Thanks, Rachel. Great. Also, if you try to keep your Q&A a bit on topic, we sometimes get people who are very excited about a particular subject that's not for today. You're welcome to throw those into the chat window directly to me, which I could add to a later webinar. But yeah, we'll try and stay on topic as much as possible, because I have sort of promoted this session about battery standards. So let's launch into it. Now, the battery standard that we're looking at is AS/NZS 5139. So once again, there's an aerial photograph of my Smart Energy Lab. For those of you who haven't been to one of these webinars before, this is where I do a lot of my training. This is also where I live. I run this facility called the Smart Energy Lab on the off-grid community that I live in near Melbourne. So this is Mount Tullibuong. So without further ado, let's just look at section 6. So we got up to talking about the battery standard yesterday in terms of the three sections 4, 5, and 6. And I indicated that those sections are very repetitive, almost exactly to the clause number. So clause 4.2.2 is almost the same as clause 5.2.2 is almost the same as clause 6.2.2. That's because we wanted you to be able to select which section applies to the battery type that you're using. Section 4 was for pre-assembled battery energy storage systems. That would be a package manufactured by to a standard and tested to a standard and compliant with the best practice guide. And so that's a very kind of limited set. Really, it's products that are like an all-in-one solution, like a Alpha ESS, eStore, like a Sonnen, like a Varta package, like a Tesla Powerwall. They're all pre-assembled BESSes because they've got the PCE as part of the product. There's no on-site manufacturer of components. You are just connecting it, mounting it, and connecting it. Section 5 was where you had a pre-assembled battery system. And a battery system contains features such as a battery management system. A pre-assembled battery system also needs to comply with the best practice guide to be in section 5. So sections 4 and 5 at the moment are only for lithium batteries compliant with the best practice guide, because the best practice guide was basically written around lithium batteries. It will be updated, but that may be some time before it's applicable. So we've moved into section 6, which is really the toughest section to be in. And I know it really rankles a lot of people. Don't blame me. This is just how the standards roll, that we are looking at a standard. We're looking at products that are often the safest products you could choose, but they're put into the most arduous part of the standard. And that's really just because we don't have adequate product standards for a lot of new tech that comes on the market. I mean, sure, a manufacturer can say our battery chemistry is the safest ever made. It's just air and water and nothing wrong can happen, but it's got to be tested to a standard before we can reference that in an installation guide. So what's covered in section 6, this is a summary slide here, is stuff like general requirements, installation requirements and hazards, and documentation and verification. So I'm going to go over those shortly, but I'm going to start up with looking at arc flash issues, because that's part of the documentation a verification commissioning area, and installation hazards. But already, I guess a few questions may have come in. Rachel?
Yes, a couple. Orb was interested in the wind turbine in the photo. He asked if it is a vertical wind turbine of the photo of Mora Mora.
Yeah, right. That one there. So bottom right corner is a Darius rotor. It's really better described as a wind sculpture these days. It doesn't rotate. It's about 35 years old, long before my time here. It was built as a kind of an experimental product, really, in its day. Darius, which is a style of vertical axis wind turbine, was a little bit popular in the 70s. One of the sort of disadvantages of a Darius rotor is they don't self-start. So it's actually got a great big electric motor underneath it to get it turning. This was not a good site for a Darius rotor. The wind was too intermittent. And so it actually used more energy than it generated because it kept on stopping whenever a gust blew through, and then it would have to start up again and the motor would crank it. So it's just a wind sculpture. But what you will see probably in a few months, if I take this photograph again, is a beautiful 70 kilowatt ground mount tracking system that's going in just below that turbine towards the viewer. So that's going to be the main power generation for the Smart Energy Lab and part of the co-op.
Yes, from Jeff. Does a pre-assembled BESS always include a PCE?
So a pre-assembled BESS, because the last S is system, means there is components that supply energy from a battery system. And so it could be, I don't know of any, but it could be a DC output as opposed to an AC output. Maybe it might be a pump controller or something. So it's possible to have a BESS that is not an inverter, but I don't know of any yet.
Richard asked if we have a list of the product standards for batteries.
Do we have a list of product standards for batteries? Yes, in fact, I had them on a slide right at the beginning of yesterday's session. I listed the four main standards that you need to consider. So if you go to my YouTube channel, Rachel will type it in the captions. So it's YouTube/Smart Energy Lab. You'll find that in episode 7, which was yesterday, I start with looking at an overview of the standards that apply to battery systems. But just to reiterate them, it's basically this standard 5139, ASNZS 3000, ASNZS 4509 for standalone power systems, and the best practice guide. Of course, there'll be a few sub-standards specific to the type of installation you're doing, but those are the main four.
Okay, and this is somewhat unrelated. It's more about panel orientation, different panel orientations in series. So Mark asks if panels of different orientations, e.g. 2E east, 2 west, be connected in series in a DC PV system running straight to an MPPT.
Mark, can I sort of answer that question in two parts? Part one is I'm going to cover this in more detail in a subsequent webinar in probably, I'm not sure if it's tomorrow or the day after. We'll be looking at modeling. Actually, it'll be Thursday because Rachel will be talking a bit about design. And so we'll cover that in more detail. But in a very simple summary, as far as our PV array standards concerned, AS NZS 5033, all modules in a series string must face the same direction, plus or minus 5 degrees of azimuth and inclination. But if you have two strings, they can actually face different directions. So you can have one string facing east, one string facing west. And if those two strings are parallel onto a single MPPT, the other requirement is that the modules are of the same type and same number. So it means you've got, if you have 8 on the east, you need 8 on the west. We'll go into more detail about modeling the performance of arrays with multiple orientations.
One more from Richard. Will you cover wind turbines at all?
So Richard, I'm really a dummy as far as wind turbines go. I've got quite a few here. I think I've got 3 or 4 wind turbines. I put a few up in my time. I'm not a wind engineer. It is actually way above my pay grade. So apologies, I won't be covering wind.
There is one more. It's I think it goes back to, I think if you, Anonymous, if you go and have a look at the webinars on Glenn's YouTube channel, Smart Energy Lab, you may find the answers there. But I'll ask Glenn and see what he says. For grid tie applications, what are the regulatory requirements in a grid outage for the solar to contribute to the battery, i.e. Alpha Smile cannot have this feature, however the Tesla can do it.
Okay, so yeah, I'm happy to answer that one. Any system that parallels with the grid must comply with our grid protection standards for inverter systems, which is AS/NZS 4777. Part 2 is the product requirements, and Part 1 is the installation requirements. It is basically, it has to island within 2 seconds. That's a requirement when the grid disconnects. Whether that system can be charged from renewable sources or not really comes down to the type of configuration you happen to have. Now, I think we covered that in some detail in episodes 2 and 3. We looked at system configuration. So I point you to that, as Rachel indicated.
Alberto asked again about battery recycling from yesterday. Who's responsible for it? End customer, installer, or original seller?
Alberto, thank you for that question, because I don't think I answered it properly yesterday. I would suggest this comes down to state regulation in Australia, and I'm not sure what the regulation requirements are in New Zealand or other countries. But for instance, in Victoria, where I live, we have an e-waste regulation, so no e-waste can go into general waste. It has to go through a proper recycling program. It's still an area that's not well supported in terms of recycling of non-lead batteries. So lead acid batteries are extremely easy to recycle because they actually have a positive cost at end of life. The lead is still valuable, so someone will pay you for them. Battery systems that to recycle have a cost. There are some limited options, but there are companies rising to the challenge, everything from just crushing them, turning them to road base, to actually separating out the materials into its constituents and then repurposing those. So I can't give you a definitive answer, but it really would fall under local regs and what the recycling requirements are for batteries. So arc flash. Now, for those who are not familiar with electrical arc flash issues, what is an arc flash and why are we concerned about it? This is a bit of a summary slide about what an arc flash is. It occurs when there's an electrical, generally electrical fault, where there is an air gap between an energy source and that can generate an arc, and that can often happen when you sort of disconnect something or short circuit something. That arc reaches temperatures up to 4 times the temperature of the surface of the sun. So like, look at that. This is straight off Wikipedia. So nearly 20,000 degrees Celsius, but it's very focused. So the temperatures of arcs are very, very high. How far they extend is based on a calculation, which we'll look at in a minute. And the material around the source of the arc is often vaporized as well and adds to that arc and the conductivity of it. So we're introducing into our battery standard 5139 a requirement to actually calculate arc flash, incident energy, and boundary for safety reasons. To give you an idea of what the units that we use are, we use cals per square centimeter. There's a calculation for joules to cals here. The amount of energy it takes to cause a burn on your skin, a second-degree burn, is 1.2 cal, and that is kind of like the threshold for PPE. So if it's equivalent to holding your hand above a candle, approximately 2.5 centimeters above for 1 second, will give you a burn of about that cal level. So that's what we're trying to avoid, that when you're working on electrical equipment or operating it, that you can receive secondary burns from that and from an arc. So the calculation in the standard, now these calculations aren't proprietary. These are actually well known for calculating arc flash incident energy. So I'm happy just to have shown these to you. I'm not actually allowed to share the standard itself because it's covered by copyright, but this is just the information available on the internet anyway about calculating incident energy. It is a shall in this standard. You shall calculate the arc flash incident energy, and it has to go in part of the recommendation or requirements for PPE. And we'll talk about PPE based on cal level in a minute. It looks a little bit complicated at first, but after all, it's really just multiply, divide, and there is a square in there. So you can do it on your phone or your pocket calculator. I will show you a spreadsheet that I've produced, and I've already shared it from yesterday's webinar. It's actually on my YouTube, episode 7. It's in the description. There's a link to it. So you're welcome to download that. It's a very simple Excel spreadsheet, and you can unlock it and change it if you wish, but it's just got all the fields locked that you don't need to put data into, so you can't mess it up easily. One of the inputs, or the inputs to that calculation that you need to know, is things like what the system voltage is. So that's if it's a battery system, we're talking about battery systems here. You need to know what the nominal battery voltage is, not the maximum, not the minimum, the nominal battery voltage. You need to know, and this is often the hardest thing to find out, the bolted fault current. Now, bolted fault current is if there is all external protection is removed and a short circuit, or 0 ohm resistor, it says in the standard, is placed across the terminals of the battery, what the instantaneous current is. Now, we're not talking about the current at tripping point of any internal protection. It's the instantaneous current. And so that will be determined by whether there is any internal overcurrent protection within the battery system, or whether it's just the internal resistance of the cells themselves. So if you've got lead acid batteries, for instance, generally, if you short circuit a terminal, there is no overcurrent protection device inside the cell. You've only got the internal resistance to limit the current. That's something the manufacturer should provide to you. So if you're buying a battery system or battery cells to build a battery system out of, you want to know what that fault current is. The arcing current is listed as half the bolted fault current. The reason it's half is because of the internal resistance of the battery is taking half of that energy. The arcing time, and this is a big one, if you don't have any internal overcurrent protection, the arcing time in the standard is deemed to be 2 seconds, which really, really increases the arc flash incident energy. If you have internal overcurrent protection within the battery system, or string protection within the battery cells, then the arcing time will be significantly less, typically 0.1 of a second, but you can even calculate it based on the current time series for the protection device. The working distance is deemed to be 45 centimeters, which is basically arm's length as a maximum working distance. And the magnifying factor is that an arc flash can be magnified based on where you install a system. So if you install a battery system in the open air, the magnifying factor is 1. But if you put it inside a room, the magnifying factor is 1.5. And if you put it inside a small enclosure, a box, for instance, it magnifies it to 3. So those increase the amount of arc flash incident energy. So no questions? Oh yes, no questions at all. Okay, so I'll keep going. I've given a worked example here, but rather than just show you the worked example, I'm going to share my spreadsheet with you, which is a little bit more dynamic.
Where is your spreadsheet?
Okay, I'll bring it up now.
Where's the?
So where is it on the? It's on YouTube on episode 7. In the description, there'll be a Google Drive share, which you can click on.
I'll post it.
Yep. So you got to go to YouTube/Smart Energy Lab. Look for episode 7, which was last night's or yesterday's one.
Yeah, and a question just popped up from Nathan, and I think Nathan, Glenn is about to answer it. How did you calculate arc potential?
Okay, I'm about to answer it. How's that? So what you're looking at now is my spreadsheet, and this is the one that I've shared on my YouTube channel. The inputs are things like system voltage. Now, I've chosen here an example of what I'd say is probably a lead acid example. I've got a large lead acid battery bank here. Its nominal voltage is 120 volts. That's one input. The other input is the bolted fault current. Now, in the case of lead acid batteries, that can be easily calculated from the internal impedance of a cell. So it's often given in fractions of or milliohms or fractions of a milliohm, and you can divide the system voltage by that to calculate the fault current. But manufacturers often list that in their data sheets. So they might say, fault current, maximum fault current, 10,000 amps. So it's for lead acid, it's actually very, very high. A large, this would probably be about a 2,000 amp hour cell, might have 15,000 amps of bolted fault current. The multiplying factor here, I've made 1.5. It's in a dedicated room, but it's not in an enclosure. And the arcing time is 2 seconds because a lead acid battery typically has no internal overcurrent protection. It's basically just cells. Now, there is a way of adding it to a lead acid battery system. For instance, if you have a midpoint isolation, as you are required with LV batteries, that could also be overcurrent protection. So you might actually have for instance, a HRC fuse switch midpoint in the string as a way of reducing the working voltage when doing maintenance on that battery system. But it also means that you now can reduce the arcing time to that of the protection device. So if it's a HRC fuse, it'll drop down to 0.1 of a second. Now, just notice what happens with the little traffic lights. If I go to 2 seconds, my incident energy is 13.3 cal. Now, I should point out, for instance, you cannot install a battery system that has over 4 cal in a residential location. So this system couldn't go in or near a home. This would have to be in a dedicated building. It's got red because it's in that moderate danger zone. In a minute, you'll see what the PPE requirements is, but it's starting to get near a beekeeper's suit in terms of serious protection, face and body. But if I put in that midpoint disconnect, which is also overcurrent protection, I can drop the arcing time to 0.1. And suddenly, look at that, it drops to 0.7, it's insignificant. So that tiny change of actually having within the string overcurrent protection massively reduces the arc flash incident energy. The boundary is the safe working distance, or the working distance at which you don't need any PPE. So if you're more than a certain distance, so in this case, you can't go within 1.5 meters of this battery unless, with a arcing time of 2 seconds. But if we put in that midpoint protection, we're down to 33 centimeters, basically just arm's length or less. That's when you need to wear PPE. So if you had a system that you can't get within 1.5 meters of it, the system operator, unless they're wearing PPE, can't even turn it off. So it's really important to understand the implications of arc flash boundaries as well as incident energy.
Richard asks which standard the arc flash calculation comes from.
AS/NZS 5139. Now that's the battery standard that we're focusing on today. It's a mandatory requirement to calculate the arc flash incident energy and boundary. You're required to specify the PPE or the personal protective equipment required based on that calculation. It should be in the operator's manual. You also need to do a risk assessment. There is a lot of documentation in this standard. For those of you who are familiar with the documentation requirements for PV arrays, I think there was about 11 sections in the PV array standard for documentation. In this standard, just in the in the operating manual, there is 26. It goes to A to Z. So there's a lot of documentation requirements. In addition, you also have to do risk assessments as well. So I guess I'm pointing out that this is quite a big step up in terms of safety, what we require when installing a battery system. And for some of you, it might be a little bit daunting the first time you do it, but many of these, many documentation requirements are quite repetitive, so you may work hard to produce the first one, but thereafter just change a few values. And hopefully this spreadsheet will aid you in doing that arc flash calculation as well.
Okay, and Stephen Zilm is asking us to plug Solar Plus because he asks, will it automatically calculate the arc flash requirement based on the battery selected?
Thank you, Stephen. So actually that's a good segue to Solar Plus. You might have noticed on my shirt, and Rachel's also got one on, but it's a bit lower down, you can't see it. We're both part of the Solar Plus team. Thank you. Very good. And Stephen's our favorite customer. So we produce software for designing and installing solar battery storage systems. We will be covering design in detail on Thursday. And so Rachel's actually going to lead this Thursday session and show how to design a system using software, using Solar Plus. So thanks, Stephen, for that little prompt. But we're still just dealing with the raw characteristics and requirements within the standard. Yes, Solar Plus always tries to be as compliant as possible, so we're always bringing it up to current standards and documentation requirements.
How do you do a midpoint fuse? So for midpoint voltage monitoring in a battery bank, it can't be in the battery enclosure, can it be on outside of box?
What is typically done in, say, a larger installation of cells is you may have, I'm looking in plan view, so this might be our positive. Sorry if you're using green. And then we may have a return string, ... meaning lots. So what you're looking at here is looking down onto the system. So let's say this is nominal 120 volt system. Now the requirement is that LV battery systems, and that really now is over 60 volts, licensed electrical work, you need to bring it up to the same requirements as an NZS 3000 as an LV system, so double insulated cables, etc. This can't be accessible to the system operator, so it needs to be enclosed. But that question around about midpoint overcurrent protection and isolation. Now, if you have a lead acid battery system, it will be potentially emitting hydrogen oxygen, so there is an explosive risk within that enclosure. It's a requirement that you have ventilation. So I'm just going to draw a plan view, an elevation view of these batteries. So here's the batteries in side view. All right, so here's our row of batteries in side view. We are required to have no arc source within 100 mils of the top of the cell. So anything below that 100 mils is okay to have something that could potentially source an arc. And the reason for that is we're also required to have ventilation to make sure that there's no gas pockets inside that enclosure. And so if you were to put midpoint isolation or overcurrent protection here, all right, so there's our HRC fuse switch. So it gives us two things. It gives us a means of breaking that string into a safer voltage level, 60 volts per string. It also gives us that midpoint overcurrent protection, which reduces our incident arc flash energy. If that was located down here, so here's our sometimes called rat trap HRC fuse switch, it's below the vent points of the cells. It can be on the outside of the enclosure as long as it meets the requirements of IP2X. You can't touch anything that's live. It could be inside the enclosure because it is only for maintenance. It's not part of a shutdown procedure. It's part of a maintenance procedure. You could even just put a fuse in there. You don't actually have to have the isolation, but it's very good work practice to do that. So yeah, hopefully that explains, Nathan, how you can include midpoint overcurrent protection and isolation within an enclosure where there is explosive gases.
Thanks, Nathan. Thanks, Glenn. Fabio asks about, no, it's a comment, is it? This standard covers BESS up to 200 kilowatt hours. What if I have a system with higher capacity? Does it still apply, for example, the rule I can't install it if the arc flash is above 4 calories per square centimetre? Sorry, my terminology is off.
So yes, you're right, Fabio. I think I touched on this the other day, that the scope of this standard, I covered scope in episode 7, is for systems between 1 kilowatt hour of storage and 200 kilowatt hours of storage, between 12 volts and 1500 volts DC. Now, if you're building a system bigger than 200 kilowatt hours, it's basically an engineered solution. You'll be doing probably a part 1 solution under ASN ZS 3000, but you may well find that this standard provides you with good safety advice. Now, arc flash, even though it's a requirement in the standard, is kind of a safety issue in any system. You don't actually have to wait for the standard to require it. So even though you're outside of the scope of this, the arc flash calculations in this weren't invented for this standard. They were existent already. And so if you know what the consequences are of a certain arc flash intensity level, you need to have the appropriate PPE, and therefore any system of any scale should also comply with that from just a basic personal protection point of view.
Okay, David asks, can the fan be located inside at the same location as the OC device?
Overcurrent?
Yes.
Yeah. Okay, so what you're talking about is forced ventilation. Maybe I'll do another diagram here just to sort of explain this one. So let's draw an enclosure. So this is our elevation view. And so we have an inlet here and we have an outlet here. Now, the requirements for ventilation are specific to chemistries that have explosive gases. If there are toxic gases, you also need to be able to contain those or remove them so you're not creating a dangerous environment for the system operator. But we're specifically looking at explosion hazards here. So this is in case of explosion hazards, and that would be typical of a lead acid system. So inside here, you've got your cells. I'm just doing a X-ray vision of the batteries, looking at cells, and the gas is basically coming out the top here. Hydrogen is the lightest element. It only goes up, so it will just go straight up. It's a requirement to have a certain ventilation rate. Now, this was previously in AS 4086, but it's now referenced in this standard as well, what the ventilation rate requirements are. It depends on the current, the number of cells, and whether it's a sealed or vented cell, and whether there is over voltage protection. But the ventilation rate can be achieved through two means. We can have what's called passive. So passive is no moving parts, basically just the aperture. So as long as the size of this aperture is calculated correctly. Oops, sorry, rub that out. Passive is just based on aperture, but active can be based on the amount of air that you have to move through that enclosure. So active requires ventilation, so active ventilation. And active ventilation, I would suggest, is not that popular because it means that you need to have a failure alarm in case the active ventilation fails. That means you've got moving parts, noise. You also need to consider that it is an arc source as well if it fails. So really, if you had active ventilation, you'd want it to be down here somewhere below where it could be a source of ignition, not at the exit point. So it is possible to do active ventilation as long as you have an alarm in case of failure.
And is the ventilation generally only for flooded lead acid, not gel, etc.?
So both require ventilation, but sealed lead acid batteries, the ventilation requirements are massively less, often orders of magnitude less in terms of the aperture size. And that's because generally the amount of hydrogen oxygen released from a sealed battery is very, very small, often only occurs during, absorption or failure, but you still need to have some ventilation.
And do any lithium battery technologies require ventilation?
I have been told that some lithiums can produce hydrogen under some conditions. I'm really haven't seen it in any documentation for any of the products I have here, so I'm not really aware of it, but it's something that you should check with the manufacturer.
And are brushless fans okay?
Well, really, once you've got the fan more than 100 mils or any source below the vents, so if you're greater than or equal to 100 mils below the vent points, then it doesn't matter whether it's brushed or brushless, but you will get better life out of a brushless fan than a brushed fan. Okay,
and there's just one more clarification requested for systems over large battery systems. Even if it's good practice not to install a battery system with an arc greater than 4 calories per square centimetre in a residential site, legally speaking, it is not forbidden because there is not any standard that officially covers the installation of such a system.
So this standard covers systems up to 200 kilowatt hours, covers residential and commercial. So I'm not quite sure if you could say that it's not forbidden. I think it is forbidden. It's as soon as this standard is referenced in ASNZS 3000 through an amendment, which was due to happen. I don't know if it's actually happened. It's supposed to happen in April, but everything's kind of gone a bit weird. But also, from a legal point of view, if there is advice on safety and you choose not to follow it and something bad happens, you don't have a very good legal position from my experience.
And there's a comment that the building code also has requirements for batteries.
Yeah. Now, we've got this strange relationship with the National Construction Code. It used to be called the Building Code of Australia. New Zealand's got a different one. The National Construction Code does actually refer to batteries in buildings and has a very onerous requirement for any battery system of more than 20 amp hours and 12 volts, I think it is. So basically anything but a burglar alarm battery requires 2-hour structural, 2-hour integrity and 2-hour ingress of fire protection, which is really, really tough. That would make it virtually impossible to install a battery system in most buildings bigger than a burglar alarm battery. You would find very few data centers and UPSs would even comply with it. So it's kind of been a strange sleeper in the National Construction Code. I believe they've kind of not taken it out until this standard's being published. And so I imagine with the next iteration of the National Construction Code, they'll just point simply to this standard and stop having this slightly outdated clause about little tiny batteries.
Okay, I'm going to paraphrase Ruth here. So sorry, Ruth, but I just want to hear what Glenn says. What happens when you add water to a lithium battery?
Well, I can only answer from experience. They don't look so good. They tend to swell up. I've had my watch get water in it once, and the top burst off it. I've had water get into some lithium cells in one of my containers, and they expanded. Basically, it's bad news.
What's the gas?
What's the gas? I don't know.
Is it hydrogen?
Well, if it's electrolysis, it probably is. I'm not a chemist, so don't try and trap me with chemistry questions. I'll just say I don't know.
Okay. What have we got here? There's a couple more. A flame-proof light's required in the room with lead-acid batteries.
Okay, so what's called sealed luminaries in the battery standard are required above batteries that have explosive gases that are emitted. So if it's within what's called the zone, and I'll even draw this again. So I bring my drawing tablet back up. Where are we? A lot of this actually comes from AS 4086, which has now been retired and replaced by this standard, and we adopted a lot of these things, is that if you have a battery system in a room, so here's a building here, this is the room, and we have a battery system within that. So there's our battery system. Those are cells. So I'll just draw little tops of all the cells. And if they emit explosive gases, so this, once again, this is where there are explosive gases. There's an exclusion zone drawn in the standard that looks like this. And that exclusion zone is greater than 500 mils horizontally. So from here to here, greater than 500 mils. Previously explained the greater than or equal to 100 mils as part of the exclusion zone, and right up to the ceiling. So all of that is an exclusion zone for a source of ignition. Now you can get sealed luminaries, basically a sealed light. So if it were to if it's an incandescent bulb and it blows, it's within a gas-tight fitting and doesn't ignite any gases around it. It's just best practice not to put lights above batteries, because maybe that seal isn't so good, but it is possible.
Oh, so David asked if back on the overcurrent protection in the midpoint of lead-acid battery systems, can a front-wired HRC fuse holder be used for the overcurrent device, say an ES-type HRC?
So hang on, I'll just jump out of this shared screen. I'm just trying to visualize what you mean, but I mean the principles of you cannot have any something you can touch with your finger if it's above 60 volts under the standard, because that's deemed to be hazardous. So as long as the protection device doesn't present any touch potential for systems over 60 volts for more than 0.2 of a second, then you could use like an HRC fuse switch, where some of them you can actually get your finger in there, some of them you can't. A better option would be to use a suitably rated circuit breaker. We now see some reasonably priced high current circuit breakers being used. I love them a lot better than a HRC fuse switch, mainly because customers don't know how to operate them. I've had them rip them off the wall thinking they're like an emergency escape handle from an aeroplane. They just grab them and pull, and then they've got a broken switch, which they can't operate their system anymore. They also are frightened to shut them. So as they start to shut them, you'll get a large inrush if you have a big inverter connected, and that inrush is a big arc, a big crack, and they hear the crack and they stop. And so they've only half shut the switch. It's just touching with, a few mils of metal. It's not properly pushed into the knife connector. And so that will arc away and damage the contacts. So, I do recommend using circuit breakers, though you can use HRC fuse switches for overcurrent protection and isolation. All right, we should have my slide up now. Good. So we've covered arc flash instant energy calculations. That spreadsheet should help you. We've also covered arc flash boundaries. That spreadsheet also covers this. This is a little more complicated calculation. Now, how do you get that information? Now, here's an example from Ep8. They provided this data for their particular battery type. So they've got a product called the Ultraflex, which is a lead acid battery. It's an advanced lead acid battery, and it comes in multiple configurations. You can have it with 1 string up to 4 strings in one Ultraflex. Now, they've listed the fault current as 4,500 amps for a 1 string and 18,000 amps for 4 strings. But I should point out that is if you can get to the battery side of the overcurrent protection device, which is actually built into the product. Now, I think they've probably done themselves a disservice. This is more the information to someone who's manufacturing their product, because from an installer's point of view, you can't access the battery side of the overcurrent protection device. It's an HRC fuse switch, which is encased. So you'd have to disassemble it to touch those terminals. So the fault current is actually really that of the protection device in terms of its time current series. It will be massively reduced. So getting the information from the battery manufacturer about bolted fault current, at this point, I've found there's still a poor understanding of what that requirement is. And if you find yourself in a position where it just seems too big, make sure that they're calculating it based on what is accessible, not what's inaccessible within the product. Here's an example of a large battery system. It's actually something that my company installed some time ago for a customer. This isn't finished. This is a construction photo. Probably you can see some of the terminals are still hanging off. If a system like this, if it was over 4 cal per square centimetre, which this would be if we didn't have string overcurrent protection, couldn't be installed in a building with habitable rooms attached. Now, this was actually in a farm shed, so even though we did put string overcurrent protection in, so it would fall under 4 cal, it still could have been installed without that string overcurrent protection because of its location. And it must be installed to fire hazard level 1, which basically means it can't be within a building containing habitable rooms, and there's some other requirements with fire level hazard 1. I want to explain a little bit about the decisive voltage classifications and mechanical protection of cables. And I mentioned this yesterday when I introduced this part of 5139, was that we're moving away from the old definitions of ELV and LV, and the installation requirements have changed based on battery system voltage. So a battery system that is over 60 volts for more than 0.2 of a second is now equivalent to LV as defined in AS3000. And that means your cable protection needs to be that of an LV system, even if the battery voltage is like 61 volts under any operating conditions. So double insulated cables, adequate mechanical protection, screen from touch to IP2X, etc. So that has kind of raised the bar in terms of safety. A question I've got a lot about the fire hazard, and I should bring up a diagram of that in a second. I think I've got it coming up. There's a requirement to have a protection against the spread of fire wherever there's a habitable room behind the wall. And people have often said, well, what about building a fire-rated cabinet? Wouldn't that solve the problem? Do we actually have to put up a fire-rated surface behind a battery system? Can't we just put up a fire-rated cabinet? Well, the answer is no, because the standard doesn't allow or doesn't consider fire-rated cabinets. It only talks about surfaces of the wall. So even though you might have a fire-rated cabinet, you would still have to have protection against the spread of fire behind that cabinet if there was a habitable room behind. This is probably a good time for me to try and explain this exclusion zone. Now, I think I've actually already drawn something for this, so let me just bring it up. Okay, there we go. And I'll just share this. Okay, so here's an example of a BESS and the exclusion zone in red. So that exclusion zone is defined in the standard as the area which you cannot have equipment not associated with the battery energy system or BESS. It's also the extent of the fire protection requirements, whether that's cement sheeting, concrete block, terracotta tile or brick. That area is the minimum that you need to have that fire protection against the spread of fire barrier established. So in practice, I've seen people use compressed cement sheeting and applied that to the wall first and then put their BESS or battery system against it. It also says that you can't have any appliance within 600 mils. So an aircon, for instance, or a hot water service, etc. But, and this was a question from the other day, you can have equipment associated with the battery energy system. So you may have, for instance, an inverter within that zone. So let's say we've got an inverter here. There's our inverter. That's okay as long as your clearances are as per the manufacturer's recommendation. You might have isolating switch. You might have some monitoring equipment as well, etc. That can be within that 900 mil high, 600 mil exclusion zone. The other requirement is that if the eave is less than 900 mils, you need to line the eaves as well. So if your eaves were at 800, you've got to line the eaves to extend 600 mils beyond the front of the BESS or battery system. So that is another consideration, particularly for single-storied buildings. Okay, Rachel, how are we going for questions?
We're good. They're caught up in your drawings, I think, Glenn. This is nice.
Yeah, I've made some pictures as well, so I'm just going to drop out of that. Whoops, there's a nasty picture. So just to reiterate, what materials are suitable as a protection against the spread of fire? The standard specifies brick, concrete, ceramic or terracotta tiles, compressed cement sheeting. And the last point is really a tough one. Materials with a fire resistance level compliant to AS/NZS 15. Actually, it's AS, it's not NZS, it's just AS 1530.1. I've had a few people email me some products saying, look, this product lists 1530 on it. Is it suitable? Actually, the ones that were sent to me weren't 1530.1. They were 0.3, 0.4. 0.1's the hard part. So you've got to even get right down to the right sub part of a standard. So 1530.1 is a fire resistance level. The other consideration is location in the case of a battery system connected to PCE, PCE being like an inverter or charge controller, is that you're required to have a load break disconnector within 2 meters of the battery system and in line of sight. And if the battery system, if the inverter is greater than 2 meters away, you need it at the inverter end as well. So I've only shown one here because the inverter is within 2 meters of the battery system. But if the inverter was 4 meters away, I'd need a load break disconnector at the PCE end as well. All right, so I think some questions are coming in there, Rachel.
Yeah, Stephen just asked, I don't know, Stephen. Glenn, did my question from late yesterday get answered with regard to using circuit breakers for isolation of Powerwall? Or does it require a separate isolation switch?
Oh, so Stephen, thank you. No, your question didn't get answered from yesterday. Apologies. So a Powerwall is a BESS and its output is AC. So the requirements of 4777 apply to the output of that. It's AC output. You don't need any DC isolation. So treat it as you would an inverter. You still need to have isolation of the AC side within 3 meters, I think it is, and line of sight. So yeah, no difference from installing an inverter and putting an AC isolator adjacent to it.
Okay, and George asks, in case we can meet UL 9540A, would that reduce the need of safety level?
George, is that the new UL for batteries in buildings? I'm not familiar with 9548. I know that UL were working on a new standard for effectively similar to our standard, which was to cover batteries in residential buildings. So I'm not familiar with it, so I can't really answer your question, George.
David, I gave you this answer the other day. What is the definition of a habitable zone? It's in the definitions of the battery standard. And like, e.g., would an entry hallway be classified as a habitable zone? Yes, it would.
No, it says hallways aren't.
Really?
So, yeah,
what about an entryway?
So
I would say anything inside the house.
Okay, let me unpackage that question a bit. So the standard doesn't give an exhaustive list of habitable rooms. It says, for example, a bedroom, I'm just trying to remember off the top of my head, a bedroom, a lounge, a kitchen, a bathroom, right?
Kitchen. Yeah, I'll tell you what they are, sure.
Yeah.
Let's keep talking.
Suitable locations may include a storeroom, utility room, garage, or dedicated room. Hallways aren't deemed to be habitable, but they are a passageway and they may be a pathway to exit. So they bring in other requirements, which is that you must have 1 meter of clearance in front of a battery system if it is located in a pathway to exit, and you can't have a battery within 1 meter of an exit. So you can't have it within 1 meter of the door, i.e. the entryway, and you can't have it in a hallway where there's not at least 1 meter of clearance in front of the battery system.
Would you like the actual definition read out?
Go.
Habitable room, room associated with a domestic or residential electrical installation used for normal living activities. For example, bedroom, living room, lounge room, music room, TV room, kitchen, dining room, sewing room, study, playroom, family room, home theatre and sunroom.
Thank you, Rachel. Yeah, so there's going to still be a bit of wiggle room. Someone will invent some new type of room, like it's my I don't know, walk-in wardrobe. Is that actually a habitable room, or is it a utility room? The principles are that if you spend time within it and there's a potential accident, it's dangerous. So that's the intent. Any more questions, Rachel?
Yeah, what was the reason a window wasn't allowed adjacent to the battery?
All right, so the other exclusion zones listed are distances from a vent that vents into a habitable room or a window. You've got to be more than 900 mils below a window or a vent that vents a habitable room. So that might be an exhaust vent from a kitchen or a bathroom. And within 600 mils of the side of a window as well. So there's quite a matrix. Now, I actually have some pictures to show this. I better bring those up so you can see a real application. So I drew this, I've jumped a few slides, but I'll go back to them because I think it's a good opportunity to sort of explain what 5139 means in terms of installation. Now, sorry, I just took this picture straight off the Tesla website. It's a picture of a beautiful looking installation, and this is kind of how customers imagine their battery system will look. Now, if that wall is not brick, terracotta, concrete, or a fire-rated material, let's say it's one of those super insulated SIP panels. It's not actually a fire-rated material, even if it's got a concrete render on it, that's not solid concrete. That wall would not deem to be a protection against the spread of fire, and there's a lounge room on the other side. So what would happen after 5139 is you'd be putting up a protection against the spread of fire. Now you might notice that I've actually moved the pot plants a bit because I needed more room. I've moved it a bit further away from the door because I need to be more than a meter from an exit. And the standard sheet sizes aren't quite big enough, so I've got to cut the sheet in half and put it above. You could even argue that I've got to fill the gaps between the sheets with some sort of fire stop material. So it doesn't look so great, but then I've got to put the signage up as well. And there may be numerous signs based on the chemistry and the hazards associated with that system. So it starts to look a little bit industrial, a little bit dangerous, and it's been one of the big criticisms of the standard. It's a little bit, well, it's very harsh on the protection against the spread of fire, but that's what it is. So what I've done is taken a few pictures around my lab and around my home to try and illustrate a practical example of location and choosing a location for a battery system in a residential application. And I've even shown this picture here, which is of a red earth BESS. That's an all-in-one system. So inside that box is a SunGrow hybrid inverter, LG Chem, M48 batteries. The whole product is compliant to test standards and the best practice guide. And so that is deemed to be a pre-assembled BESS. If that were attached to a wall with a habitable room adjacent, there would still need to be a fire barrier, even though it looks like a well-protected enclosure. But there is this one little, I call it the get out of jail free clause in 5139. If you're 300 or more from a wall where there's a habitable room behind, you're not required to have a fire barrier. So this particular system could actually, because it's designed to be freestanding, could be just pushed 300 mils away from the wall, and that exempts you from that requirement of that fire barrier. And I jokingly would say it's a great place to store your fuel cans and your firewood as well. This is an example from my place. This is my home. I've got a lot of the systems I test. I use them just to learn about them. So this is an Alpha ESS system, the Smile 5, on the south side of my house. Now this was installed before 5139. There is a bathroom behind that wall. The wall is straw bale. Don't make any jokes about the 3 little pigs, please. And it's rendered with earth. Now, it's not a fire-rated material. Even though it's pretty tough, it actually meets a fair level of fire protection. It's not deemed to be one of the materials listed in the standard. So it's got a whole bunch of problems now. That sheet of plywood, that form ply, isn't a fire-rated material. It's also too close to the window. And I would require a barrier extending 600 mils wider and 900 mils higher of a fire-rated material, which would basically cover that window. If I were to do it again, I'd push it right to the corner of that wall to get 600 mils away from that window. This is the same system, but just looking down the side of the house, looking for other locations. So this is actually me walking around my house, trying to find somewhere to put a BESS or a battery system. Now, that's a driveway, so the potential for impact from a vehicle is a consideration. There's no actual requirement in 5139 for bollards, but mechanical protection is covered under ASNZS 3000. So if there's a likely impact based on the location and there's an electrical hazard, you still need to have appropriate mechanical protection. In the case of a battery in a garage, that may well be bollards. This driveway is not wide enough to put bollards in. I wouldn't be able to get the car in. But the bigger problem is there's so many windows. Remember, I have to be more than 600 mils horizontally from a window and more than 900 mils below. So there's nowhere on that eastern wall that I could put a battery system. Let's look around the back of the house, a wider view here. The rear of the house is quite wide. I need at least 1 meter of clearance in front of that BESS, because that is the exit path from the house, is out that door and past the battery system. And so I'm lucky I have got a meter of clearance, but if it was a small block where the fence came quite close to the battery system, I still might not be able to install it there. Down the other end, gas bottles, no. There's other appliances, can't put them next to there. So there's basically nowhere on the south side of this house other than where I put it. What about on the western side? Underneath that shaded area, possibly. I still have to stay 600 mils from a window. So there's probably one location along that wall that I could put a battery system. Incidentally, I'm actually planning on putting one there. And I've got to still consider that access. Is there 1 meter of clearance if I put it there? Well, in this case, yes, but only just. 1 meter is a lot. So around the front, what's the north side of the house? And it's sunny. So putting a product in the sun is generally not a good idea for most battery types, but there's just windows everywhere. So there's absolutely nowhere there that I could attach it to a wall So I'm really down to about 2 places on my house. And my house is a freestanding house with lots of space around it. So it was actually really hard to find anywhere to put a battery system. Any questions, Rachel?
Yeah, there's a few popping up. I think this has just been answered, but George might like a bit more info. There is a requirement in 5139 for batteries not to be exposed to generalised sources of heat. Does this mean that they cannot be installed anywhere in direct sunlight?
Well, so that's kind of a bit of a sweeping statement. So some battery types actually are very tolerant of heat. So take your sodium nickel batteries. They operate at 260 degrees Celsius. The maximum operating temperature of the electronics, I think, is around 70 or 80 degrees. So if they were within an environment that was within the manufacturer's recommendation, that would be okay. But if you're looking at, say, a lead-acid battery, it ages very quickly with heat. A lithium battery can shut down or become unstable with heat. So it really comes down to the product itself, where it can be installed.
Okay. Ruth asks, does it have to be resting on the ground? Perhaps strap it above the bathroom window on south wall?
Another gotcha. Battery system needs to be under 2 meters. So the top of the battery system can't be above 2 meters. So that would kind of limit you how high you could put it up the wall.
Okay, what IP rating would the battery or inverter need to be rated for outdoor usage?
To some extent, IP rating, you need to consider the environment. For instance, if you're within the new protected zone under AS/NZS 3000, so you're within sort of like 30 degrees of the eave, then you're not deemed to be in direct rain, so your IP rating can be quite low. I think IP 54 or so. Once you get into areas where rain can fall on it from above, you're up to like IP 65. Then if you've got an area where people are doing wash down of their vehicle, you're probably up to IP 67, where flooding might occur, IP 68. So it's still an environmental consideration. You can't just say outside per se.
And Richard asks, is there a reason fuses, HRC or otherwise, are used for DC battery circuits rather than circuit breakers?
Mainly because they're a cheap way of getting very high current overcurrent protection. So you get a fuse that costs you sort of $10 or $12 that can interrupt thousands, or its KA rating can be 10,000 or 100,000 KA, 100,000 amps of interrupt capability. And when you're looking at lead acid batteries, particularly, they do get up into the tens of thousands pretty quickly in terms of their KA rating required. Whereas a circuit breaker will be much, much lower than that generally. But there are circuit breakers that can break at very high fault currents, but they tend to be more expensive. So I guess the popularity of fuses is because of price. They both can achieve the same outcome. But the problem from my perspective of fuses is that the operation of them as an isolating device is problematic for many customers. Thanks to everyone who attended today's webinar. Tomorrow, we're going to talk more about load characteristics and how that affects the design of a system, particularly a standalone power system, but also hybrid systems with battery and solar on grid. Hope to see you there.